Okay. So what was the homework? Oh, does somebody want to hit the third white button on that thing? It'll make the lights less glare up here or something. All right, so we wrote something last time, didn't we? What did we write? So we wrote, so we did define decimal to binary. And this guy is going to be a lambda that's going to take in a decimal number. What did I call it, n or something? All right, and then what are we going to do? We're going to keep dividing that guy by dividing that guy by 2, looking at the remainder. As soon as the remainder is 0, we're done, right? And we're building up a list. We're consing stuff onto a list, so we're building up a binary number. All right, so we'll ask the question, if equals n 0, we just return the empty list. Because we're consing a whole bunch of things onto our, we're building a list, we're constructing a list. So the end of a cons must be a list, so we'll throw the empty list when we're finally done. Otherwise, what are we going to do? We're going to cons something onto our list. What are we going to cons? We're going to cons the current value, and what was it? Was it modulo? That guy? So n modulo 2 onto the front of the list, followed by decimal to binary of divide n2. Did that give us integer division?
It's quotient. I never use quotient.
Quotient n divided by 2. So that's what we'll cons together. So like that.
So this is how you do it without a helper then?
Well, this is
what we did in class last time. You did a helper.
Oh, did I?
Yeah.
What helper did I give you?
You just had a helper that
You just had to
created a new list.
Empty list.
Yeah, you like pass the helper an empty list and then use that to cons everything on.
Really?
Yeah.
Oh. Well, no. Why did you need the empty list? How did I solve it last time?
Because you are not as good as today.
Well, no. How did I? Guys in the doorway. If any of you miss Shoddy. So, John, you see that the thing on outside of Dr. Locklear's door?
Yes.
That's the banner.
What do you want?
Look straight up at the ceiling where you are. Turn around. You see the ugly thing up in the ceiling?
The crack?
No. Turn around and look up-ish.
Yeah.
You see we have those old things and no lights coming through?
Yep.
Right? We want to cover that with like a little droop so it looks cool.
We can try that.
You know what I'm talking about?
Yep. So just kind of.
Yeah.
All right.
And then we'll get more of those if it works. All right, good luck. All right, so so why did I make a helper?
This is what you did.
To pass it to empty list. So instead of asking if n is equal to 0, you and then have the empty list. You don't have that in the other one. You just pass it to the empty list.
Oh.
You basically did the same exact.
I didn't do this piece. So if we have like the value 5, for example, we pass 5 and we ask, is 5 equal to 0? It's not. So what are we going to do? We're going to cons 5 mod 2 onto decimal to binary of 5 divided by 2. So 5 mod 2 is what? 2 goes into 5 2 times with a remainder of 1. And we're building a list that's going to give us a 1 there like that. And then what are we getting? The 5 gets passed through, so 5 divided by 2 is 2. Is 2 equal to 0? Nope. So we cons 2 mod 2. So 2 goes into 2 one time. 1 times 2 is 2, remainder 0. So we're consing that onto the front of this guy. So we have that guy. And then we're calling decimal to binary another time. So decimal to binary of, this will be 2 divided by 2, which is going to be 1. Is 1 equal to 0? Yeah, so actually this guy is not going to work as is, because if I say, well, we'll just keep following it. So it's 1. Is 1 equal to 0? It's not, so we'll cons what? We'll cons 1 mod 2. How many times does 2 go into 1? 0. Remainder 1. Actually, we're consing that onto the front. Like that. Actually, it is going to work. Then we take 1, quotient 2. How many times does 2 go into 1? 0 times. Call decimal to binary on that. So this is 0. Is 0 equal to 0? It is. So we'll boil down to the empty list here, which will finish off our cons. And we're looking at that value. But I think we actually built this in reverse here. So if we switch it around and we say we're dealing with a 6, this would have been 6 mod 2. 2 goes into 6 3 times. The remainder is 0. Then, no, this will work. It's correct. So if we want to test this decimal to binary, passing it a 6.
Let's see. Yeah, it's in reverse.
Yeah, it is in reverse. So that means we're still going to need a helper for this to do it the final right way. So I guess I gave you 2 different helpers. One that passes the list in so we can build it in reverse. The other one that, so the one I gave you last time, I kept passing a list. It took 2 parameters.
But can you just put the cons, like reverse the 2 list in the cons?
Well, I can, oh, I see what you're saying. Can I just do this?
Yeah,
I could.
then it should be.
Yeah, then it'll work. I'll just build the list in reverse.
You need a space.
What am I doing? All right, so this is going to cons that guy. The result, oh, no, because this has to be a list. The second parameter of a cons always has to be a list.
You can use a cons to create a list from an element.
Well, I can create list to create a list from it. So I could wrap this guy, then this guy just starts getting more difficult. So I can wrap this guy in the list version of this. Kick this down a thing so I can read the code at the end. So this is the first element of my cons. This is the second element of my cons, which is the list version of that value. It'll keep wrapping it.
Yeah.
So I would have had to cons it onto the empty list in order
Or you
to.
can use a
Yeah.
scan, but
So bottom line is you could either pass around an empty list and build it in reverse, or you can use a helper. So we can call this guy decimal to binary helper. That's probably what I called the one last time.
yeah,
Mhm.
exactly.
You can just go back to exactly what you had before.
Yeah.
So it's-
And then reverse it.
Well, you didn't even reverse it.
I didn't last time because I'm going to show you the second version of this time, just so you have it. Both of them are effectively doing the same thing. The one where I passed in the list, we built the list backwards because we were passing the list around, consing onto the list we had. This one, I'm building a list through cons So I'm consing the modulo onto decimal to binary helper of quotient n2. And then we're going to define decimal to binary. And this guy will take in, he'll be a lambda n, and he's going to return the reverse of decimal to binary helper of n. So there's our, so same thing. The one from last time, we passed the list around and built it in reverse. This one, we're not passing a list around. Instead, we needed the helper to actually do the reverse.
There's actually less lines in code in the one too.
Doesn't matter.
Just for the sake of everybody, can you go over what reverse does? Because that's not something that you've introduced yet.
Reverse is a list.
Thank you.
So reverse of 1, 2, 3 would give me the list 3, 2, 1. Reverse is a list.
You have a lot of them, didn't let us know.
Didn't you just ask me last night if you could use reverse?
Yeah, and you said,
Or you could write it yourself?
you said,
Yeah.
well, the way you were saying it was as if you were hinting that we should just write it ourselves.
No, which is fine.
That's what he always says.
So, yeah.
Well, so, you know,
You have to
But
do.
yes, I did ask.
yeah, so define my reverse to be a lambda that takes in a list. And what's this guy going to do? It's going to keep, you know, it's going to build a brand new list that is the old list in reverse, right? So what am I going to do? I'm going to say if null list, boil down to the empty list, otherwise cons car of list onto my reverse of cooter of list. Oh. What? This will cons the first element of the list onto my reverse of the cooter of the list. This is the rest of the thing. It's my list empty, so this will start off by consing a 1 onto, oh, I am building it right in the same order. So I'm actually going to have to wrap this guy in a list too. So really I have to use append.
Can you put the car of the list second?
Same thing as we had before. If you're using cons, the second element always has to be a list.
What I did for writing mine was just kind of what we did last time with like passing an empty list.
Yeah, and you can build it in reverse.
building onto that.
Yeah, but that wouldn't be something you can just pass something directly to. You could do it with a let rec. That wouldn't, well, you could do it with just a let because you don't need to call it recursively. We're going to write it. So we're going to append the list version of, actually we're going to say append my reverse of cooter LST onto the list version of car So I'm using the append function to pull this off, which allows you to glue two lists together. I think I showed append last time, right?
Nope. Well,
Really?
you did mention it, yeah. Never
I
mind.
don't think you
You
necessarily
didn't-
showed us, but you put it in the notes.
Yeah,
Alright.
you did mention it.
Yeah. So, and it just glues two lists together. So I'm saying my reverse is always going to return a list because at the very end it returns an empty list. And I'm going to append that onto the list version of the car. So if I have the list 1, 2, and I append that to the list 3, I get the list 1, 2, 3. And we could have used the same trick here for the decimal to binary to do it without a helper as well. So that's our version of my reverse. So we could have said that there and used my reverse to solve the problem instead of the built-in reverse function. All right, so what was another question on the homework? So we got decimal to binary.
And then it was binary to decimal.
Binary to decimal. Okay, and don't we also have a decimal to hex?
Yep, and then
Okay.
hex to decimal.
All right, do we want to stick to all binaries first? Or do we want to stick to,
You binary.
you want to do binary to decimal next?
You have to do the two completions too for that, and it's gonna be the last one.
For 2's complement?
Yeah.
Yeah. Well, let's do the conversion ones first. My understanding is the 2's complement was the one that was the hardest.
Yeah.
Is that okay? So let's go ahead and we'll do. So you want to do binary to decimal next? Define binary to decimal. This guy is going to be a lambda that's going to take in a binary value. So let's call it bin, something like that. And what is the and we'll go ahead and do it with helpers, because one of the things when I was talking to the group last night is I said make a lot of helper functions. So we'll call this guy binary to decimal helper. This is going to take in a binary number as well as a current place value, and then probably also a sum, because we're going to have actually we don't need to take a sum, we could just build the sum. So we're going to take a bin and a place. Because remember, when we convert binary to, let's get the notes open here. If we're converting a binary number to a decimal number, and we have a number, I'll just go ahead and put it in list format so it looks good to us. So if I have 1, 1, 0, 1, something like that as a list, and we want to convert this guy to decimal, this guy is in the 1's place, 2's place, 4's place, 8's place. Make sense? So in order to use the place, the first thing I need to do is I need to be able to reverse this list. And that's where my helper comes in. So I'm actually going to call it on 1, 0, 1, 1. That way I can treat this as this is the 1's place, the 2's place, the 4's place, the 8's place. All right, so right off the bat, let me just kill that off there. I'll say define binary to decimal to be a lambda that takes in a binary value. And what I'm going to do is I'm going to call binary to decimal helper, passing it I'll use my reverse, passing it my reverse of bin along with the first place, which is the 1's place. Good? Does it look good?
I think so. We put it up.
All right, hold on. We got to pause the lecture before you leave. Zoom. Okay, so I'll go ahead and call my reverse on this guy. So binary to decimal helper, I'm going to finish writing here in a second, but here's the original. I'll take in my list that representation of a binary number, and then I'll go ahead and pass the reverse version of that guy to binary to decimal helper along with the very first place that I have. All right, so that's effectively what I just passed in. The reverse of my original list and then the number 1. So I want to go through, I'm going to ask the question, is this the empty list? It's not. So what am I going to do? I'm going to add the multiplication of my place, which is 1, times the car of my list. And I'm adding it to what? I'm adding it to whatever binary to decimal helper returns for the cooter of my list, and, which is the reversed list, right? And place times 2. Make sense? So ask the question, if null bin, if I'm out of things, what am I going to be adding on to my sum? I'm going to add on a 0. That's my endpoint. Else, what am I going to do? I'm going to add some stuff. What am I going to add? I'm going to add the multiplication of the car of bin times place onto binary to decimal helper cooter of bin times place 2. That make sense? So this guy is binary to decimal. Oh heck, we'll just reverse it. So we'll do the binary to decimal of the decimal to binary of 6. That should give us a 6.
Could you take out my reverse and just put it in reverse, just so I could see what it would look like? Just for a split second, and then just Control Z.
See what would look like.
Just,
With
It's
this?
just it's just the word reverse.
it's basically like calling a function that is already written.
What?
Like reverse is a built-in function in Scheme.
I got that part.
Oh, sorry.
Yeah, so I mean, isn't that what you wanted me to do?
I guess I'm looking at in the binary to decimal.
This guy?
Yeah. Oh, okay. Okay. That's good.
I mean, it doesn't matter which one you use; they're functionally equivalent.
Yeah, I was just thinking for some reason that you would put bin inside of parentheses
Oh,
if you were using reverse.
nope. I'm applying this function to this list, and that function reverses that list, just like reverse reverses the list. All right, so this is kind of the proof by induction of this guy. We binary to decimal of the decimal, the binary of 6 gives you 6. They're reverses of each other. All right, so questions about that?
I don't think there is a need to having the reverse because based on the size of the list, you know actually what the power it is.
Oh, it does need to be in reverse the way we're doing it here.
Yeah.
You could count down, you could figure out what that far left bit is power-wise based on the length of the list. Yeah, you could do that. But why? We can just always start with 1 and then multiply by 2, multiply by 2, multiply by 2. Then we don't have to worry about it. But you're right. Yeah, you wouldn't have to reverse it, but reverse is a pretty small price to pay.
I use the length, so I don't use the reverse.
Yeah, but if you're using the length, so in this case, let's just use that as an example. If we use the length of this guy is 4, right? You would then need to take, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So you have to take 2 to the power of length minus 1, 2 to the power of length minus 2, 2 to the power of length minus 3 if you're calculating this to be more generic instead of just for binary, because we're going to have to do something very similar for hexadecimal, right? Hexadecimal, this is the 1s place, this is the 16s place, this is the 256 place, this is the 4096 place, so on and so forth. So, yeah, I mean, it's just the math of it. Yeah. So you can calculate it, but I think this is.
Yeah, for machine might be.
Yeah, efficiency-wise, you probably don't want to do a whole lot of reversing of lists and stuff like that for, but. That's true, but that's something we'll talk. Actually, did you in the reading? Did you have Little Indian and Big Indian, or is that not something you read yet?
What? No.
Endian, Endian.
No.
Still no. This is a big Indian. Shiva would be smaller, right? All right, so no, this is Endian. Endian. It has to do with byte order. We'll talk about it today with because Chapter 2's MIPS processor stuff. So we'll talk about that with that. But bottom line is, a microprocessor could choose to work with a byte backwards. It's kind of a false way to present it because actually it's byte order, not bit order for big endian versus little endian. But the way you can approach a number is you can decide either to start from the left or start from the right in an architecture. Programmers typically aren't going to have to deal with it. Okay, so let's say we're good with that. Next.
Can I ask a random question?
Sure. How random?
Scheme like used in any big applications, or is it more just like a good way to understand?
Well, I think the answer to both of those is yes, but then the follow-up is going to be, can I give you an example of a big application? It's probably not going to be software applications that you end up hearing about because it's going to be more in scientific. It's used a lot, and probably not by the name Scheme. It's probably mostly used under the guise of Lisp. Scheme's a superset of that. But the Lisp language, this language we're basically looking at, is used heavily in artificial intelligence applications, and really probably some data science stuff. Now, given that one of the reasons we're using it in here is because of how simple the language is. I know the parentheses and things like that are, can start getting a little confusing, but Scheme and Lisp are actually pretty good examples of what we're going to be looking at later today with like an assembly language. So we're looking at the MIPS assembly language, which is just like any other assembly language. And when we think about a CPU is made up of a whole bunch of little tiny magic tricks that in and of themselves don't do that much, right? Does the car of a list do all that much? Gives you the first element of the list. Well, what good is that? Well, if you use that with a bunch of other things, you start solving real problems. So we're using a language that kind of acts like a CPU from a number of magic trick perspective. And we should follow up with him. There was a student from a couple of years ago, 3 or 4 years ago, I think. Sam, I'm trying to think of his last name. It'll come to me at some point. He went and got a job doing Scheme, making just tons of money, like 150 grand a year or something like that in the Midwest, doing Scheme development. So somebody wants it out there. Okay, so next is, what do we want to write? Decimal to hex. Okay, so what we probably need to do is we need to give ourselves a function that's going to help us convert from a number to a letter and vice versa, right? So we're going to need, if we think about this in terms of Java, let's say, we're going to need a version of char_at, and we're going to need a version of index_of. So index_of lets us search through a list to give us the index of the location of a particular value. Make sense? So why don't we actually write those generic primitives just in case it might be handy for us later on. And then we'll write the hex specific call to that. We'll think of it as like a helper. So let's go ahead and let's define a function called index_of. And this will be a lambda that takes a list as well as I'll call it a search term. No, search char. Search char. We'll call it search char. All right, so it takes a list and a search char, and that will return the first position in that list where search char is found, or what does index_of typically return, like in Java? If it doesn't find it, what does it return? -1. All right, so index_of, we're looking for this guy inside of this list. So if we kind of show us our, throw that in the notes just so we can design it in here. So we have index of, and let's say we have the list 0, 1, 2, A, B, C, something like that. If we were searching for a 0, this would give us a 0. If we were searching for an A, this guy should give us a 0, 1, 2, 3. That's where A lives in there. If we are searching for a Z, this guy should give us a -1. Make sense? All right, so that's what index of is going to do. That's the problem it solves. I give it a list of things I want to search for, and then I give it something that I want to, I give it a list of things I want to search through, and I give it a value I want to search for, and it gives me the zero-based index in that list of where that value is first found, or a -1 if it was never found. Make sense, the problem we're solving? All right, so that's what index of is. So what we'll do is we'll ask the question, if null list, if I'm out of stuff to search for, boil down the -1. Hopefully we're starting to see some patterns here. We're pretty often saying if null list. If I'm out of things to look at, do my default move. Okay, so if I've looked through everything in LST and I haven't found anything, I'm going to return -1. Otherwise, we're going to need a counter. So we could do this with something called a let, but let's do this in our the vein that we've been doing stuff in. So I'm going to say define index of helper. We'll keep just doing helpers for everything. Index of helper is actually going to be what I've started writing here. And when I call index of, so index of helper is going to take in a list, a search char, and the current pos, the current place I'm looking for. You can actually pull this off with you could pull it off just doing math, and I might adapt it to that, but we're going to make it obvious with the count because the first place we're going to search for is bucket 0. So what this guy is going to do is going to be a lambda that's going to take in a list and a search char. And what he's going to do is he's going to call index of helper, passing it that exact same list, that exact same search char, and go ahead and get the ball rolling with that 0, the first place he's looking. Make sense? Go ahead.
Do you always have to put your helper before?
I don't think so. I think this, I mean, it's a multi-pass interpreter, so I think it goes through and sees everything first. All right, so if I'm out of stuff to look for, -1, done. Else, I might have something to look for. So I want to ask another question. If equals car list search char, if I found it, boil on the curpos. Otherwise, call index of helper on the cooter of list, the same search char, and here I'm going to kick this down a line so it can. And plus curpos 1. Now, let's test it real quick and then we'll go back up and look at it. So I'm going to say index of, I'm going to pass it the list, what, 0, 1, 2, A, B, C. And let's say I'm looking for that 0. I think I'm going to have to quote that, maybe not. So I found the 0 at bucket 0. It found the 1 at bucket 1. And it found the, I do need to quote this, because if I just put A there, it's going to look for a variable named A and scream at me.
You have to have.
Yeah, so 0, 1, these are integer literals. Can't have variable names with that, but you can have a variable name with a guy like this. So this should find this at 3, right? Expects a number as second argument given an A. Okay, so we can't use that guy. We need to use that guy.
What did you just change?
It's actually equal
E-
question.
yeah.
Or like the whole word.
No, this one exists
Oh,
too.
really?
And what's the difference?
Single equal sign will let you do numbers. EQ question mark will let you do, I think it's any primitive type. So it's numbers and
I think it's equal.
there's 4 actually. There's EQ, there's EQV, that's equivalent. Equivalent, I think, will work for strings and anything below it. And then there's an equal, and I always used to say equal basically checks bone structure. So equal will allow you to compare two like lambda expressions for equivalence to each other. But I suppose one thing you can do kind of goes back to your comment about efficiency, is you could just say, I'm always going to use equal. And it will work. You are putting that thing under the microscope if you're going to use equal, and that takes more horsepower to do, but whatever. So pick your poison, but since we're still dealing with a primitive type, char literal, EQ will work. Yeah. Questions? All right, so that's index of. Let me go ahead and give myself a char at the same time. Now, keep in mind what we could have done here is if the real challenge on why we needed to pass the cur pos along here is, can we always just say +1? It's the special case of it being at bucket 0. If it wasn't at bucket 0, we could actually just add 1 and create a summation all the way through. But I think it would make it a lot harder.
Are we doing hex to decimal right now, or decimal to
Neither.
hex? Okay.
We're giving helpers for both of them.
Okay.
Yeah, so I haven't even started those. I'm giving myself 2 little tools to use for both of those.
Just the way I did it was completely different.
But
That's
the
why.
final for index.
Well, it's not. It's not completely different. I promise you it's not completely different. I'm just breaking it down to smaller helpers. I haven't even started either of those functions because I'm doing helpers that will do the mapping. This is the piece that's going to do our mapping between an A and a 10 in this case. And char at is going to do our mapping between a 10 and an A. Go the other direction. So we'll define char at helper.
Is there a reason you do the helpers first? Does it read it linearly?
When she just asked that question.
Sorry. Did you? Oh
Yeah.
my gosh. I'm so sorry.
Well, it wasn't like just. It was like 7 minutes ago.
That's still really pathetic.
The answer to the question is it doesn't matter what order you put them in. It does 2 passes. It finds it. All right. So define char at helper. It's going to take a lambda. This guy is going to, just to show you what char at is going to solve. Char at solves this problem. So if I pass it that, well, here, let's just do this. If I give it that and I give it a 0, it should give me the 1. If I give it a 1, it should give me a 2. If I give it a 3, it should give me the A. Give me the value at that index instead of tell me where that value is found.
If we give you 6, this should yell to you.
Yeah. So we won't really error check for that. But yeah, if you say, hey, give me the, bucket 78, then the all right, so that'll be off the end of it. So we'll assume we use it appropriately. So we're gonna have char at helper. This is gonna take in a list and a pause. Actually, we're not gonna need helper for this. We can just do it directly. So if, again, we're assuming our list that pause is not greater than the size of our list. We're not error checking this because we're lazy. So we're going to say if pause, if equal pause 0, then we'll just boil down to the carve list. Else call char at coder list minus pause 1. So if I say char at and I say give me the char at bucket 0, oh, my index, oh yeah, here it is. That's my char at bucket 0 is the one. I called them out of order because I hadn't scrolled down on my screen. If I say char at bucket 1, it'll give me the 2. And then char at bucket 4 will give me my B.
Can you try 6?
Yeah, it'll actually what it'll do is
78.
if I say 6, it'll never, well, it'll eventually get down to 0. Then we'll try to take the car of an empty list. And actually, I think you can take the coder. Can you take the coder of an empty list?
That's a dangerous thing.
No.
No. Okay.
Yeah. So it'll fail after. Yeah.
5.
Oh, I didn't put it in 6 yet.
Yes, we should,
So it'll fail on the coder call.
we should give the same error.
Oh, as soon as they hit the 0, it actually gave the error on the car call. Oh, because we only want one off the end. If we go farther, it'll end at the coder. All right, so that's char at. So now I have the ability to give me the character that lives at a particular bucket. If we treat lists as arrays, it gives me the character that lives at a particular bucket in an array, in a list. It also allows me to say, find me the location of a particular character inside of a list. And let me show you how that can be helpful for us. So I'm going to define map hex to des. And this guy is going to be a lambda that's going to take a hextet. Hextets are hexadecimal digits. Part of the vocabulary of hexadecimal, 0 through 9, A through F. We have digits are decimal, the decimal vocabulary, 0 to 9. Octets are the octal vocabulary, 0 to 7. And then bits are the binary vocabulary, 0 and 1. So these are hextets. So give me a hextet. And what am I going to do? I'm going to return the decimal equivalent of it. If you give me an A, I'm going to give you a 10. If you give me a B, I'm going to give you an 11. If you give me a 3, I'm going to give you a 3. Make sense? So that's going to be handy for us for our conversion methods. So what's this guy going to return? He's going to return index of, passing it so that list and that value. So if I say map hex to decimal and I pass this guy an A, he gives me a 10. If I pass him a C, he gives me a 12. If I pass him a 2, he gives me a 2. That make sense? Now, do you understand why we created index of and char at here? These guys are more general purpose. I just happen to be using index of here with a very specific list that I'm passing it, right? These are the hextets associated with hexadecimal. 0 to 9, A through F. I can just as easily say map, I don't know, base 36 to decimal and pass it the whole alphabet after 0 through 9. Okay? So it's nice to have index of and char at as kind of primitive functions that we write because those might be handy for us to do for other things. Because today we're going to be writing some MIPS functions using scheme, and you never know when we're going to have to search through a list for something or we're going to have to get a certain element of a list. Actually, char at kind of already exists in scheme. There's a function, I think it's called listref, that will allow you to get an element from a particular bucket of the list, but who cares? We gave ourselves char at. Or whatever. We don't even assume it's a char, so it's not even a well-named function. Really, it should be called element at. Yeah.
So, when you're doing that list there of 0 through F,
Yeah.
how come you don't have to put a tick mark next to A through F? How come it just took it as is?
Because the whole thing is quoted.
It's a sand.
Yeah. I think I could actually. I think we saw last time. If I did put it in here, that would throw it off because that is now going to store as part of that list an extra value called quote. Yeah. So now the A I think would be at 11. I'm pretty sure actually. Let's test that. I'm actually intrigued. Oh, it just didn't find it. Oh. Is that gonna?
No.
Yeah, it just doesn't find it because of the quote before it.
If you search for the quote, what happens?
Oh, see, it's just, I think, do we need to quote a quote? I think we might need to quote a quote. I think it might be that.
No, it's not the correct.
Yeah, I think the quote is, we might be able to do this.
Please go up to your index of.
So that's going to quote A. Can I just quote nothing? Yeah. I think it's just a special keyword in it, and storing a quote is just a bad idea.
Okay.
What were you asking?
Can you go up to your index again?
This guy?
If you are not using EQ, if you're using.
Oh. I think So if we do the whole catch-all bone structure thing,
Yeah.
equal, and then we go back in and do that, and we say we're searching for
For the A.
an A.
What happens if you put it in
No.
parentheses?
If I put what in parentheses?
The A, so to make a tick mark, and then.
You mean quotes?
No, this is string.
Or you
I'm
mean,
putting up above.
oh,
After
oh.
Would that change anything?
So you want me to put
A tick mark?
like
yeah.
that?
No, put the A in between.
Oh, well, that'll just be the list A. So, I mean, this is the element 9. This is the element list containing A.
So would it still give you -1?
It will, because, I mean, if I'm looking for an A, it's not going to find an A in there.
It's gonna find the list A.
Well, it'll look at the list A and say that guy's not an A. He's a list that holds an A.
Not found.
But if I was looking for the list that holds an A, using equal, it should find that guy.
Should.
With equal, it should find that guy.
So the
Everything's
Map
checking
hex 2
function
decimal.
what I done
is
without
wrong.
it.
No, hold on. We're overlooking something.
Alright, totally opened up a can of worms.
No. This might be showing a bug in our index of.
This is why we need to do more error checking.
So, I look for an A. If the car is equal to the value, return curve pause. Great. Otherwise, index of helper passing it the rest of the list, still passing it my list A, and passing it curve pause +1.
You can try
But
debug and see what's.
Well, eventually, so I mean, really, it's this. Equal for the list A and the list A should be true.
It is true.
So when the car of my list is this guy, let's do it this way. Equal that guy and the car of the list containing the list A. Yeah.
It is.
So.
Quote happen. Like,
Oh, it is. It is. Thank you. That gives you the 10. So when we put that quote in here, do we just break the rest of the list?
Yeah. In the list, it doesn't need a quote.
Well, I think it's worse than that. I think it's just not correct to have a quote. If I say that quote like that, that's going to give me the list containing a list whose first element is a quote and whose second element is a actually this is like this is the quote literal.
What is?
I think the quote literal is sort of kind of real loosely like the empty string.
What is this?
So that means that I would have to say the car of the cooter for that guy to get a match. Yeah, so for right now, I'm thinking just don't put quotes in the middle of your lists.
Yeah, that's the wrong thing.
That is bad news bears.
Did you end up changing index of it all?
No.
No. Index.
Well, I did actually change it to equal right now, but that wasn't the
I
problem.
think you can change it back.
You can put it as EQ or better. EQ or stronger. Pick your poison. All right. So, and then we're searching for an A like that. That should give us the 10. All right.
Correct.
Cool. So that's map hex to des. And then we're going to define a map des to hex. And this guy is going to be a lambda that's going to take a digit as a parameter, right? That's the vocabulary of decimal. It's going to take a digit as a parameter, and he's going to return charat of this dude on digit. So map des to hex, passing it a 10 should give me an A. There's my A.
Can you remind me why you put the word map in front of these?
Oh, why I'm naming it that?
Yeah.
I mean, I'm mapping from an A to a 10. I'm just calling it. You're maybe thinking about the map function that's built into, so you don't want me to answer that yet because that will let me give you much harder assignments. But I'll probably end up using it today at some point anyways, so it'll be fun. Actually, I am going to use it today. I'm going to use it with our the cooler version of our 2's complement. I'm going to map flip bits across.
Nice, Maddie.
Oh no, it'll be a fun one. It's good. All right, so now I can go from A to 10 or 10 to A. That's a nice little tool to have for doing my conversion stuff. All right, so now I need to write decimal to hex, and I need to write hex to decimal. All right.
That's not what you just did.
No, I can't do a whole number yet. I'm not dealing with this as the 1's place, the 16's place, the 256 place. I've done most of the heavy lifting. Now I'm effectively writing. In fact, I can just steal this guy up here. So we'll say binary to decimal and binary to decimal helper. Let me just steal those two and we'll modify them. So this is going to be hex to decimal helper, hex to decimal. This guy will take a hex value, and we'll call this hex to decimal helper. We'll call my reverse on hex. That way we can start with the 1's place being in the far left, times 16 times 16 times 16. All right, so let me just change the variable names in here. That's hex, that's hex, that's hex, that's hex, that's hex. All right, now for decimal hex to decimal helper, we can't just take the car of that hexadecimal value and start doing math with it, because the car could be a letter. If the car is an A, I want that to be treated as a 10. Okay, but if the car is a 3, I want that to be treated as a 3. So what I can do here is I can say I want to call hex. So what, map hex to decimal, map hex to decimal on that guy. So go ahead and give me the car of my hex list. It's going to be 0 through 9, A through F. It's going to be one of those. Go ahead and map it to its decimal equivalent. So I get a 0 through 9 or a 10 through a 15. Make sense? So that's the only, besides variable name changes, the only modifications I had to make here was make sure I map this value. And now I could use this. We'll actually write a generic one here in a second where I can go from any base to decimal and decimal to any base. Because by passing in the base, I know what to change that to. So I happen to be using hexadecimal now, so I have hard-coded a 16 in there. But if I wrote base 2 decimal, and I had this guy take in another parameter called base or radix, R-A-D-I-X, then I can just multiply by the base there. And that will always, and I would just have to make sure my map hex to decimal was, I would maybe name it differently where I'd have the entire alphabet in there, 0 through 9, A through Z, and then it would do the mapping for me. All right, so this is hex to decimal helper. So if we say hex to decimal of BAD, my favorite hexadecimal value, we get our 2989.
Correct.
All right. Questions on hexadecimal?
Are you gonna put all of this in Slack?
I'm going to immediately delete it when we're done with it.
It's so rude.
This is going to be like so bad.
That is
Did
go.
you do decimal to hex?
I'm about to write that. So now, decimal to hex is the same thing as decimal to binary, the little loop-de-loop. So here's my decimal to binary and decimal to binary helper. So we'll call this guy decimal to hex helper. And we're going to be modulo 16. And we're going to make a little other change in there, but we'll come back to that in a second. This is going to be decimal to hex helper. And this will be 16. This is decimal to hex. And we'll call decimal to hex helper. Okay. So now we're consing something onto my list, but I need to make sure I map that to the hexadecimal value of this. So I need to call map decimal to hex. Whatever this value is, make sure it is the hexadecimal version of it. So if it's a numeric 10, I need to turn it to an A. And it's the A I will cons onto my running list. Make sense? And then decimal to hex helper, quotient, blah, 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 6. Okay, this should be good. So then we'll call decimal to hex, passing it 2989. And this should give us BAD. All right, questions on that one? All right, so what was the last question? I know it was two's complement. What am I doing with it?
Just
Oh, for any what I say, 4 bits?
function that encodes 4 bits to complement values.
Okay, so what is the largest? So first of all, if I'm dealing with 4-bit numbers, what is the range of values that can be represented in 4 bits? I'm sort of asking that, but I want a different answer than that. What is the purpose?
To the 4.
What is the purpose of 2's complement?
Oh, to get a negative.
To represent negative numbers. So if I have a 4-bit value that I'm saying if it's going to be a 4-bit signed value, what do I mean when I say it's a signed value?
As negative.
It's capable of holding positive and negative values, right? So 4 bits can hold what range of values? 4-bit signed numbers can hold what range of values? Yeah, -8 to +7, as opposed to 0 to 15, because we get half of those. And does the book talk? Did I talk about sign and magnitude and 2's complement and stuff last time, or that was something you read about? Read about it. Okay. So what's the weakness of sign and magnitude or 1's complement, and why is 2's complement better? You can ask yourself the question either way.
You can do subtraction.
That's the second part of it. But
-8.
Because you have the same number twice.
yeah, so sign and magnitude, which is just saying treat the left bit as either positive or negative and just do normal binary for the rest of it, that's going to have 0 represented twice. +0 and a -0. Not the end of the world, but again, if we're talking about efficiency, hey, I have 4 bits to work with here. I want to represent as many possible values with 4 bits as possible, right? Similarly, if I use 1's complement says just flip all the bits, right? Well, I can do 1's complement to represent those as well. It's kind of like sign and magnitude. It just looks a little bit more encoded, because you're not just looking at the last 3 bits for value. You're looking at these weird number representations, like the series of 4 bits is equal to the negative value of this. Problem with that is identical. You have a positive and a -0. We don't need 2 different ways of talking about the number 0. When we think about the vocabulary of decimal numbers, 0 only exists once, right? We don't say 0, 0, 1, 2, 3, 4, 5, so on and so forth. We only need to represent it once. 2's complement happens to give us the power of not having to represent 0 once and instead, or 0 twice, and instead we get to represent an extra value, an extra negative value. So instead of -0, we get a -8, for example, in our 4-bit language. So -8 to +7, those are our 16 unique values that we can identify using 4 bits. That makes sense? And as Alexis pointed out, we also have the added benefit of, oh wow, it also allows us to do subtraction through addition, which is another performance benefit. So it gives us a larger representation pool, and we can do stuff that would be otherwise much more difficult. So we're going to have a function called flip bits. All right. So we'll say define flip bits. This guy will be a lambda that takes a binary number, a list of binary values as a parameter. And what I'll do hold on. This is going to be awesome. Hold on. You're throwing off my... All right.
You have like 10 openings around this.
It's going to be awesome. Just trust me. There. So if I call flip bits on 1, 0, 1, 1, I should get 0, 1, 0, 0. There's my 0, 1, 0, 0. So that's what you were asking about earlier, this map function. So what the map function does, that's not how I heard it. Everybody in here heard her ask about the map function, right? All right, well, so let me explain what this does. So What map does, it's a built-in function scheme. It allows you to take a function that has one parameter and map it over every element of a list. So I'm saying I want to take this function and I want to apply it to each individual value of bin. What does this function do? It takes a single parameter and asks the question. If it's a 0, boil down to a 1. Otherwise, boil down to a 0. Is this guy a 0? Nope. He boils down to a 0. Is this guy a 0? Yes. He boils down to a 1. Is this guy a 0? No. He boils down to a 0. Is this guy a 0? No. He boils down to a 0. So I applied this function, a lambda, which is an unnamed function. I applied that function to every element that is inside of bin. So I applied it to this guy, and this guy, and this guy, and this guy. All right, so now let me write it the way I would have expected you. So that is flip bits cool kids. All right, so this guy's going to be a lambda that takes in a bin, just a list, right? And I'm going to be building a new list, with each element being the opposite of the previous guy. The logic is almost going to be identical. So our pattern, if we're saying if we are done looking at stuff, boil down to the empty list so we kind of finish our cons train. Otherwise, what am I going to do? I'm going to cons something. What I'm going to cons on is going to depend on what the car looks like. So if equals car bin to 1, then what am I going to do? I'm going to cons on a 0 to flip bits of cooter bin. Else, I'll cons a 1 onto flip bits of cooter bin. What'd you do? I have an extra. All right, so that's my question. If the car bin is equal to a 1, do this, else do that. So that's the 0, 1, 0, 0. Isn't this one much more cooler, kidsier?
That's a syntax sugar.
Yeah, syntactic sugar. Because really, this logic right here is not effectively what I'm doing right here. So map makes that life a little easier for that. Whenever you need to apply a atomic function, a function that takes one parameter to every element of a list, map makes that kind of an easy thing to do. All right, so that flips the bits. Now, the last thing that we need to do for 2's complement is add 1. Okay. So define 2's comp to be a lambda that, and how did you have it come in as a 4-bit value, or did you have it come in as a decimal value?
I'm doing this.
Okay. 4-bit? All right, well, we can do them both. All right, so lambda, so this will be a bin, well, if we want the 2's complement of this guy, we actually need it to come in as a decimal so we know whether it's negative or not. But if you pass it a 4-bit and we assume that it is, actually, no, 4-bit will work fine. Because you did it as 2 steps. You did, hey, if I need to do a 2's complement, we'll just do it. Otherwise, just encode the value if it's positive. So, or we'll assume that's what you did. Is that what you did? You only called 2's complements? I'm not, I don't even know anymore. My eyes have been bleeding for the last 14 hours.
But last class you said assuming that you're including the
Okay. That's fine. That's what 2's complement works on anyways. It'll always work on 4-bit values. Well, it'll work on a number of bits.
Yeah,
So we'll call that bin, all right? And so for 2's complement, what are we going to do? We're going to flip the bits of that guy, right? So how do we do that? We call flip bits of bin. So now that guy's bits are all flipped, right? Now we need to add 1. How do we add 1? Okay, so first of all,
I'm so excited.
why don't we write it in the way that's going to infuriate you? Is that always a good way to start?
Yeah.
And
I like to end on a happy note. If he makes you mad first, then you forget about it.
Logic.
So we'll go ahead and turn that flipped bits guy back to a decimal value. We'll add 1 to him. And then we'll turn him back into a binary value.
I thought about doing that, but I seriously thought you were gonna get mad if I did that.
Well, this would be inefficient, but it will work.
16.
Here, I'll spread it out a little more. So 2's complement, going to take in a binary number. We'll go ahead and convert that binary number. Well, we'll flip the bits of that binary number right there. Then we'll convert it into its decimal equivalent. Then we'll add 1 to it. Then we'll convert it back to its binary version. Flip the bits and add 1. That make sense? So, 2's comp of, let's say, let's do this as the number, so this is the number -7, presumably. We're trying to represent the number -7. So we're passing it the binary value 7 and saying, encode yourself in 2's complement. So this should be, flip all the bits, should be 1, 0, 0, 0. Add 1 to it, 1, 0, 0, 1.
And that'll work for any size then, right?
Yeah, work for any size right now. Make sense? So, what if we tried to write it by hand? We tried to do the addition. So we want to write a function that adds 1 to a binary number. Right? Okay, well, what does that mean? Let's look at the pattern of this. Add 1 to binary. So if I have something that looks like that, let's make my list. So we'll have 1, 0, 0, 1. That'll be a good one. That way we have to jump at least once. How do we add 1 to this number? Well, we start at the left-hand side, correct? Actually, I'm going to do this just so when we reverse it, it looks reversed. All right. So similar to what we did with the whole place, I might want to reverse this right off the bat. So I say 1, 0, 1, 1. So now I have it backwards, okay, because I'm going to be operating with a carry. Because initially, I had a carry of 0. And it's going to be easier for me to work with the front of the list, right? So we're going to call this guy my carry bit, which is 0. So, and then what I'm adding is a 1. Okay? So what am I going to do? I'm going to look at the car of this list, which is a 1. A 1 plus a 1 plus a 0 is a 2. With a 2, what am I consing? A 0 with a carry. So a 2 gives me a 0 with a carry. A 3 gives me a 1 with a carry. All right? So 1 plus the 1 I'm adding plus this 0 will give me a 0 with a carry. So I'm going to cons a 0 onto whatever gets returned by calling on the coulter, but now I have a carry.
And 0.
You only want to add one the first time.
Only adding to the first time. So it's going to be a 0. And from that point forward, it's always going to be a 0 there. It's my carry bit that's going to be the guy that might screw things up, right? So what do I do here? I look at the car. The car is 0. What do I do with that? I say 0 plus 1 plus 0 gives me a 1. That comes down to a what? A 1 with the coulter of the list is 1, 1 with carry 0, and that guy's a 0. So my helper function will be the guy who passes the 1 in the very first time. From that point forward, he's always passing in a 0. And then my carry bits just do the rest of it, and I cons it. Kind of see how this pattern's working? So then at the very end, so we'll just keep following this guy here. I'll have a 1 there. I'll have a 1 there because we're not doing anything to it because we're adding zeros all over the place, so it's just going to stay the same. Finally, we're going to have the empty list. So what we end up having in the very end is a 0 consed onto a 1, consed onto a 1, consed onto a 1. That's what we'll have there. And then, is that in the right order? I need to reverse it. Flip it around. So this number, if I'm adding 1 to this number, this guy will become a 0. This guy goes to a 1, and everything else stays the same. We could also look at it from that perspective. The pattern is to find the very first 0 from the right and make that a 1. All the ones before that become zeros. But we're doing it with the actual math here. So we come back out here. We go ahead and let's write we'll call that guy 2's comp wimpy up there. It is a little bit of a cop out, but probably would have saved you some time. So define 2's comp. This guy will be a lambda that takes in a, actually we're going to call this 2's comp helper. So this guy is going to be a lambda that takes in a binary number, takes in a carry, and takes in an adder, let's call it. And what's he going to do? He's going to ask the question, if null bin, return the empty That's going to be the end of my cons. Otherwise, what am I going to do? I'm going to be doing some consing. So I need to take the car of this guy, I need to add the carry, and I need to add the adder. If it's a 3, I'm doing what with it? I'm consing on a 1 and passing. It won't be a 3 in our current case, but I'm passing. If it's a 3, I'm consing a 1 and passing a 1 as my carry. If it's a 2, I'm consing a 0 and passing a 1 as my carry. If it's a 1, I'm consing a If it's a 1, what am I consing? A 1 with a 0 carry. If it's a 0, I'm consing a 0 with a 0 carry. Make sense? So I can do this in a series of if statements, or I can do it with a conditional. Do you guys look up conditionals at all? A cond? Do you want me to do it that way, or you want me to do it with ifs?
It's the same.
So we'll go ahead and say cond if, actually a let would be the nicest thing here, because then I could just keep referencing the variable, but I won't do that. So I'll say if the car of bin, that guy, plus carry, and I actually think plus will work with more than 2 parameters, but I'll link it again. Plus adder. So the general definition of the plus operator is it adds 2 operands. So I'll say the car of bin plus carry, and then I'm going to take that value and add it to adder. That's going to give me an answer. Okay? If that value is equal to 3, what am I going to do? I'm going to cons a 1 onto whatever's returned by 2's comp helper, 2's comp helper of could or bin, 1 for my carry, 0 for my adder. If it's a 2, 0 carry, 0 for adder, and I'll cons on a 1. Actually, no, this is consing on a 0, right? If I added them together. If it's a 1, I'll cons on a 1. Hold on. Let's slow down because I skipped one. This guy here, if it's a 3, I'll cons a 1 with a carry. If it's a 2, I'll cons a 0 also with a carry. Right? Still carrying. If it's a 1, I'll cons a 1, no carry. Else, cons a 0, 2's comp helper, could or bin, 0, 0. Define 2's comp to be a lambda that takes in a bin. And I'm going to call 2's comp helper, passing it bin, passing it my carry, and my original add 1. That's not the right answer though. Hold on. It's got to be another if statement here. Oh, I'm not reversing it. Oh, I'm not reversing it. I need to reverse it. My reverse. Up in. Go through, do our math. Then we need to flip it back around in the end, right? Okay, I'm passing it 0, 1, 1, 1. So this should turn into, well, I'm never flipping the bits either. Hold on, I need to call this the correct way. Everybody relax. Flip bits. So I'm going to flip the bits of binary, reverse it, pass it to my 2's comp helper with an initial no carry, and I'm adding a 1. Do all my math, flip the bits back, well, not flip them back, reverse my final answer, and that should be my thing. So what should this guy ultimately be? If I flip all the bits, this is going to be 1, 0, 0, 0. Adding 1 to it should give me 1, 0, 0, 1. So wrote all the code, just didn't know how to call it. That's... All right, questions about that? Does that solve all the homework problems? Go ahead.
Kind of a random thought question. What?
Tread, you say tread lightly?
I said don't do it.
Don't do it!
You guys did the MapDes.
So you know how map only allows lambdas with 1 parameter? What if you wanted it to support 50? Up to 50. Okay, go ahead.
I'm scared.
You should be.
Okay, so what I was thinking about doing for this one without, I had like the same idea of going through each one and having a carry in the adder. But what I was confused with / trying to accommodate for was you only want to add 1 the first time. And so I was trying to define my own Boolean. Is that something that you can do?
So you were trying to basically create a flag that said, if I already changed it, don't do this again?
Yeah.
And is that for, were you doing the actual addition or were you doing the mapping pattern of looking for the first 0? Were you actually doing math or were you looking at a binary number starting at the right-hand side and say, I'm going to keep changing 1s to 0s until I finally hit a 0. When I hit a 0, I'm going to change that to a 1, and I'm not going to touch another thing. Not that way. Because that's the pattern. Well, that's the pattern of add 1, isn't it? If you look at a binary number, let's say I'm adding a 1 to that. I start from the right-hand side, so we would reverse it for our thing, but I'd start at the right-hand side, and whenever I see a 1, I'll flip it to a 0. So here, let's just say this. So what should the answer to this be? It should be 1, 1, 0, 0. That's what that guy added with 1 added to it is. So I start at the right-hand side, but if I hit a 1, make it a 0 until I finally hit a 0, then I flip it to a 1 and never touch another thing. Scheme will make me finish going through the list, but I'll have to mark that I've done my damage. I've shot the arrow, and now I don't have to do another thing. So I'll hit this first 1 here, and let's just go ahead and reverse it. So I'll say 1, 1, 0, 1. So now I'm going to start walking through this guy. I'm going to have to maybe pass in we'll just pass in a false, like a Boolean. I have not done it yet.
How I did it was like having it be, I called it like
Mhm.
whatever. And so it was, yeah, I think it was false, and then after you do it, add for like the rightmost side.
Yeah, well, I mean, this is going to accomplish that same thing, so I'm kind of showing you a flag. We passed this flag through there. Since I haven't changed it yet, what am I looking at here in the car? I'm looking at a 1. I'm going to cons on a 0. Keep going. Don't change my false. So now I'm passing it, the 1, 0, 1, still a false. I look at the car. What am I looking at there? I'm looking at a 1. So I'm going to cons on a 0. Actually, let's do it this way. So I'll cons on a 0, and then I'll pass the rest, still a false. Now I'm at this level. I look at the car. It's a 0. Have I done anything yet? No, because this is false. So since I haven't done anything yet, I'll cons on a 1, called on the rest of my list, but now I change that to a true. I'm only allowed to do anything when this value is still a false. So now I get this last thing. I can just say, if it's true right now, just take the car and move on with life. So the car of that guy is a 1. Then I'm going to hit the empty list, put it all back together, and then reverse it. You know, so that's the pattern of adding 1 to binary. But I effectively did the flag thing that you were talking about, where you can just pass that extra value around and say, I'm always going to check that variable. If he says it's okay for me to do something, I'll do it. Otherwise, just go. Just skip it. I mean, is that what you're trying to accomplish, is just giving yourself the checking with the manager type thing?
Yeah.
Like a for or a while?
Technically, loops do exist in Scheme, but not the way I teach Scheme. So you're not allowed to use loops. I think the function is called loop.
Sounds good.
Yeah, but you get to use recursion. Recursion's fun, right? Think about how much you got to do recursion this last week. All right, so that's the homework assignment. So I should immediately delete all this. All right, you want this up on Slack? All right. So let's take about a 45-second break. Let's do about, what time is it? Let's come back at 8. Let's do 11 minutes.